Have you ever just stopped and wondered, how on earth does your computer do all that stuff at once? You know, you're streaming music, you've got like 20 browser tabs open, a file is downloading. How does it not just completely fall apart? Well, today we're pulling back the curtain on the invisible traffic cop that makes it all possible. Process synchronization.
No, really, think about it for a second. You have all these different programs or processes running at the same time, and a lot of them need to use the exact same information. It's like having a bunch of people trying to write in the same notebook at the same time. How do you stop it from becoming a totally chaotic mess?
Well, the answer, and kind of the hero of our whole story today, is something called process synchronization. This is the secret sauce, the set of rules that brings much-needed order to all that potential chaos inside your machine.
So, what is it really? At its heart, it's just about coordination. You know, when you have multiple processes that need to share the same piece of information, we call these cooperating processes. You need a manager to direct the traffic. Without that manager, you get what's called data inconsistency, which is just a techie way of saying your data gets totally messed up and fast.
Okay, so if synchronization is the hero, every good story needs a villain, right? And in our story, the villain is this sneaky, really dangerous bug known as a race condition.
So a race condition is exactly what it sounds like. Imagine two programs are literally racing each other to get to the same piece of data and change it. The final result, the correct answer, depends entirely on who gets there first. It's totally unpredictable, and that is what makes it so incredibly dangerous.
All right, that probably sounds a bit abstract, so let's make it super simple. Let's say we have a counter, and it starts at 0. We've got two processes. We'll just call them A and B. All they have to do is add 1 to the counter. So 0 plus 1 plus another 1, the answer should be 2. Simple, right? Well, you'd be surprised.
So here's how it all goes wrong. Watch this. Process A reads the counter. The value is 0. But then, and this is the key part, the system switches tasks for just a split second. Now it's process B's turn. It also reads the counter. And what does it see? It still sees 0. So now both A and B think the number is 0. Process A finally gets its turn again, calculates 0 plus 1, and writes 1 to the counter. Great. But then process B does its calculation, 0 plus 1, and it also writes 1. It just overwrote A's work. The final result is 1, not 2. And just like that, our data is wrong.
And this is exactly why programmers absolutely hate race conditions. They are a total nightmare. You see, this error might only happen one time out of a million. It depends on that perfect, unlucky timing. So trying to find it and fix it, almost impossible. And the consequences can be huge, from a tiny error in a spreadsheet to a full-on system crash.
So how in the world do we stop this from happening? Well, the solution is actually pretty elegant. We create a protected zone. We find that little piece of code that touches the shared data, and we put a big digital bouncer in front of it. And this special VIP area has a name.
It's called the critical section. The best way to think about it is like a room with a one-person-at-a-time rule. If a process needs to work with that shared counter, it has to go into the critical section. And if someone's already in there, sorry, you gotta wait outside until they're done. Simple as that.
Now, to make this work properly, any good solution has to follow 3, let's call them golden rules. First up, mutual exclusion. That's our one-at-a-time rule we just talked about. Second, progress. This just means the system can't get stuck. If the room is empty and someone is waiting, you have to let them in. You can't just lock the door for no reason. And third, bounded waiting. This is about fairness. You can't let one process just wait in line forever. Everyone has to get their turn eventually.
You might think, wow, that sounds kind of complicated to get right, but it's totally possible. There's this classic algorithm from way back in 1981 called Peterson's solution. It's a really cool piece of computer science history because it proved you could satisfy all 3 of those rules for 2 processes with just some clever coding. A fantastic early example of how this problem was tackled.
Okay, so we've seen what can go wrong with just 2 processes, but what happens when things get even more complex? To really wrap our heads around that, we're going to look at a famous thought experiment, one that's been a staple in computer science classes for ages.
It's called the dining philosopher's problem. Picture this. You've got 5 philosophers sitting around a circular table. Now here's the catch. There are only 5 chopsticks on the table, one placed between each philosopher. To eat, any philosopher needs 2 chopsticks, the one on their left and the one on their right. So they just sit there, thinking, and then eating, and then thinking again. But what do you think happens if all 5 of them
get hungry at the exact same time, and they all try to do the same thing to start eating. What's the worst that could happen?
Here's the disastrous scenario. Imagine every single philosopher decides to pick up the chopstick to their left, all at the exact same moment. So now every philosopher is holding one chopstick. Okay, but to eat, they need the one on their right. But where's that chopstick? It's in their neighbor's hand. And that neighbor is waiting for their right-hand chopstick. Everyone is waiting for someone else who is also waiting. Nobody can eat, nobody can put their chopstick down. They're stuck forever. This catastrophic gridlock has a name. It's called a deadlock.
And this isn't just some weird story about philosophers, right? This is a perfect analogy for how computers work. The philosophers are your programs, your processes, and the chopsticks? Those are your system resources, things like your CPU, your memory, access to a printer. The dining philosopher's problem shows us exactly how a bad synchronization plan can cause the entire system to just freeze. Everything grinds to a halt because every process is waiting for a resource that another process has.
All right, so we've battled race conditions and we've sat down with some very hungry, very deadlocked philosophers. So what are the key things to remember from all this?
Okay, let's boil it down. Takeaway number 1, whenever you have processes sharing information, synchronization isn't optional. It's absolutely necessary to prevent total chaos. 2, remember the villain, the race condition. It's that unpredictable bug caused by bad timing. 3, the solution is our safe zone, the critical section, which is protected by that one-at-a-time rule of mutual exclusion. And finally, if you mess up the rules, you can end up with a deadlock, where your whole system just freezes up.
And that's really it. That's the secret to how our computers juggle so many tasks at once. It's all about this careful dance of synchronization, bringing order to what would otherwise be complete chaos. Hey, if you found this explainer interesting and you want more deep dives into how all this tech stuff really works, do us a huge favor and like this video, share it, and of course, subscribe to Tech Talk 101. Thanks so much for tuning in.